We'll start in 1 minute. In a few minutes, we'll start section 10.3 on polar coordinates, but first we'll finish section 10.2. We got up to arc length. Recall from chapter 8, section 1, the length L of a curve C defined by y equals k of x for values of x between a and b. The arc length, or the length of the curve, is the definite integral of the square root of 1 plus the square of the derivative of k from x equals a to x equals b. So recall the Leibniz notation. Since y equals k of x, dy dx is equal to k prime of x. And if you square dy dx, that's the same as squaring k prime of x. So an alternative formula for the arc length is using the Leibniz notation. The length is the definite integral of the square root of 1 plus the square of dy dx from x equals a to x equals b. So now we suppose that a curve C that's described above is traced once from left to right by parametric equations, x equals f of t and y equals g of t, for values of t from alpha to beta. From left to right means that as t increases, x increases. And if x increases, dx dt is positive. That is, the derivative of f prime of t is greater than 0. Okay, so if the curve is traced out from left to right, then we can transform the arc length formula in terms of x and y to the third variable t. So specifically, the definite integral of the square root of 1 plus the square root of dy dx as x ranges from a to b is equal to the definite integral of the square root of 1 plus the square of dy dt over dx dt, dx dt dt from t equals alpha to t equals beta. So you'll recognize from last time we used the chain rule to show that dy dx is equal to dy dt divided by dx dt. And in terms of the differentials, dx is equal to dx over dt times dt. Okay, but this is equivalent to a simpler formula for the arc length. This is the definite integral of the square root of dx dt squared plus dy dt squared as t ranges from alpha to beta. So you can check this out in the textbook, Theorem 5 on page 653. Okay, but let's find the arc length of the curve x equals the square root of t, y equals t to the second over 8 plus 1 over 4t for values of t from 1 to 9. Okay, so we're just going to use this formula. We need to know what the derivative of x is with respect to t. So if x is the square root of t, dx dt is 1 over 2 times the square root of t. And we also need to know what the derivative of y with respect to t is. So dy dt is t over 4, and then minus 1 over 4t to the second. This derivative for y with respect to t, let's write it as a single rational expression with a common denominator of 4t to the second. So if we just multiply t over 4 by t to the second over t to the second, we'll get, in the numerator, we'll get t to the third minus 1, and in the denominator, 4t to the second. Okay, so the arc length is the definite integral. T is going to go from 1 to 9. And then we just have the square root of the square of dx dt. So we're going to square 1 over 2 times the square root of t. And we're going to add that to the square of dy dt. So we're going to add the quantity t to the third minus 1 over 4t to the second squared dt. And now all we have to do is evaluate that definite integral for the arc length. So if you already worked this out, you saw that this works out really nicely. So we'll do the algebra and arithmetic inside the square root. Hey, when we square 1 over 2 times the square root of t, we're going to get 1 over 4t. And then when we square the rational expression, t to the third minus 1 over 4t to the second, in the numerator, we're going to get t to the sixth minus 2t to the third plus 1. And then when we square the denominator, we'll get 16t to the fourth dt. Okay, a common denominator inside the square root. Let's write this as a single rational expression with a common denominator of 16t to the fourth. Okay, so we'll multiply 1 over 4t by 1 in the form 4t to the third over 4t to the third. So multiply the numerator 1, multiply that by 4t to the third. Multiply the denominator 4t by 4t to the third, we get 16t to the fourth. And then we'll add that to the other rational expression. Yeah, I'll have to start writing smaller so I don't run out of space. But inside the square root, well, we can add the numerators, and the numerator will become t to the sixth plus 2t to the third plus 1 over 16t to the fourth dt. And inside the square root, both the numerator and denominator are perfect squares. And when we take the square root of a perfect square, I'll go ahead and write it in. So the numerator, t to the sixth plus 2t to the third plus 1, that's the same as squaring t to the third plus 1. And in the denominator, 16t to the fourth, that's the same as squaring 4t to the second. And then finally, when we take the square root of a perfect square in the numerator, we'll just have t to the third plus 1, in the denominator 4t to the second. And let's write the integrand as a sum of two terms. Since we have a single term in the denominator, t to the third divided by 4t to the second is t divided by 4. And then 1 divided by 4t to the second. For now, we can write it as plus t to the negative 2 over 4. Then we can find antiderivatives. Okay, an antiderivative of t over 4, t to the second over 8. And an antiderivative of t to the negative 2 over 4 is negative t to the negative 1 over 4, or minus 1 over 4t. And then we'll evaluate that from 1 to 9. So when t is 9, we get 9 to the second over 8, or 81/8. And then minus 1 over 4 times 9, or 1 over 36. And then from that, subtract 1 squared over 8, or 1/8, minus 1/4. Okay, I'll leave the rest of that for you to do. Just add and subtract the fractions. Hey, the next topic in section 10.2 is surface area applied to parametric curves. Recall from chapter 8, section 2, if a function y equals capital F of x is positive and has a continuous derivative, then the surface area generated by rotating y equals f of x about the x-axis for values of x between a and b is this formula. The surface area is the definite integral of 2 pi times capital F of x times the square root of 1 plus the square of f prime of x dx, as x ranges from a to b. Okay, so we suppose that the graph of capital F of x for the x interval from a to b is traced once by parametric equations, x equals f of t and y equals g of t, for values of t from alpha to beta. Then the surface area can be transformed into this formula. It's the definite integral of 2 pi times y times the square root of dx dt squared plus dy dt squared, as t ranges from alpha to beta. Equivalently, since y equals g of t, that's what we want to put here anyway, we want to put what g of t is. Okay, so let's try that out on this one. Find the surface area generated by revolving the parametric curve about the x-axis. Okay, so x equals 2t minus 3 and y equals 8 minus 2t, and t is ranging from 2 to 4. Okay, we need to know what the derivative of x with respect to t is. That's just 2. And the derivative of y with respect to t is negative 2. Okay, so the surface area is the definite integral from t equals 2 to t equals 4. 2 times pi times what y is. Y is the binomial 8 minus 2t. And then in the integrand, we multiply this by the square root of the square of dx dt, or 2 squared, plus the square of dy dt, which is the number negative 2 squared. So it's just a little bit more arithmetic. So inside the square root, we have 4 plus 4, which is 8, so the square root of 8. Okay, the square root of 8 is 2 times the square root of 2. So if we multiply the constants, 2 pi times 2 times the square root of 2, and bring that constant out front, we get 4 pi times the square root of 2, and then times the definite integral from t equals 2 to 4 of 8 minus 2t. So just a couple of more steps. An antiderivative of 8 minus 2t is 8t minus t squared from 2 to 4. Okay, so 4 pi times the square root of 2. When t is 4, we get 32 minus 16, or 16. And then from that, 8 times 2 minus 2 squared is 16 minus 4, or 12. So this equals 4, and then when we multiply that by 4 pi times the square root of 2, we get 16 pi times the square root of 2. Those are, since it's area, it's square units, whatever the units happen to be. Okay, now let's go ahead and start section 10.3. This is the section on polar coordinates. And the first sentence, the Cartesian coordinate system is not the only system that can be used to plot ordered pairs of points in a plane. Every point in the xy plane can also be represented by using the polar coordinates r theta. So this ordered pair r theta represents a point in the xy plane. Okay, so the next couple of sentences describe how that works. Given a point in the xy plane with polar coordinates r theta, the absolute value of r is the distance that the point is from the origin, that is the point 0, 0. Well, in x and y coordinates is 0, 0. And theta is the oriented angle formed in a well-defined way by the positive x-axis. And in the polar coordinate system, the positive x-axis is also referred to as the polar axis. Okay, and the line that passes through the origin O and the point. Since I interrupted myself, let's read this paragraph again. So given a point in the xy plane with polar coordinates r theta, the absolute value of r is the distance that the point is from the origin. And theta is the oriented angle formed in a well-defined way by the polar axis and the line that passes through the origin and the point. If this is still not clear, then our examples will probably clear everything up in a few minutes. Theta, if theta is greater than or equal to 0, then the angle is formed by pivoting counterclockwise from the positive x-axis, with the origin being the pivot or the pole. So if theta is greater than or equal to 0, the pivot is counterclockwise. If theta is negative or less than 0, then the angle is formed by a clockwise pivot. If r is greater than or equal to 0, then the point is plotted r units from the origin along the pivoted ray determined by theta. And if r is negative, then the point is plotted negative r units from the origin in the opposite direction of the pivoted ray determined by theta. Hey, have you encountered polar coordinates before? Okay. All right, we'll plot the points given the polar coordinates. Okay, the first pair of polar coordinates, the r value is +2, and the angle, or the theta, is pi/6. Okay, so the positive x-axis is the polar axis. Theta is positive pi/6. So we're going to pivot counterclockwise an angle of pi/6 radians, which is equivalent to 30 degrees. So the ray, we refer to that ray as theta equals pi/6. That's the size of this angle. And since the r value is 2, then from the origin we measure 2 units. And so this point right here, the polar coordinates of that point are 2 pi/6. Okay. So in the next example, r theta is 3 pi/2. Okay, theta is positive pi/2. So from the polar axis, the positive x-axis, we rotate counterclockwise 90 degrees, or pi/2 radians. So that's pi/2. And then from the origin, we measure 3 units in the direction of theta equals pi/2. So 3 units. Okay, so this point has polar coordinates 3 pi/2. In the next example, the polar coordinates are -1 pi/3. Pi/3 is equivalent to 60 degrees. Since it's positive pi/3, we pivot counterclockwise 60 degrees, or pi/3 radians. And since the r value is negative, we extend the ray in the opposite direction and measure 1 unit. So the length, or the distance from the origin to this point, the distance is 1. It's the negative of -1. So this point in the third quadrant has polar coordinates -1 pi/3. Okay, then the fourth example, the polar coordinates are the square root of 2 and -pi/4. So from the positive x-axis, since theta is -pi/4, we rotate clockwise pi over 4. That's equivalent to 45 degrees. So clockwise, label that negative pi over 4. The R value is positive. So from the origin in the direction of negative pi over 4, we measure out the square root of 2. So that length is the square root of 2. Okay, do you see how that works? Well, every point in the xy plane corresponding to polar coordinates also has rectangular coordinates. So we'll use the same 4 ordered pairs that were given in polar coordinates and convert them to rectangular coordinates. So for this, we can use right triangle trigonometry. So I'll just redraw the right triangle. So we want to convert the rectangular coordinates 2 pi over 6 to rectangular coordinates. Did I say that right? Convert the polar coordinates to rectangular coordinates. We're going to use this right triangle. So the hypotenuse is 2, and the angle is pi over 6. And the x-coordinate of that point is the length of the horizontal side of that right triangle, and the y-coordinate is the length of the vertical side. Okay, so cosine of pi over 6 is adjacent over hypotenuse. So cosine of pi over 6 is x over 2. And so the x-coordinate is 2 times the cosine of pi over 6. We know what the cosine of pi over 6 is. It's the square root of 3 over 2. And so 2 times the square root of 3 over 2 is just the square root of 3. That's the x-coordinate. And then the sine of pi over 6 that's the opposite side over the hypotenuse, y over 2. So the y-coordinate is 2 times the sine of pi over 6. Sine of pi over 6 is 1/2, so we get 2 times 1/2, or 1. So as an ordered pair in rectangular coordinates, we have the ordered pair, the square root of 3, 1. And that is equivalent to the rectangular coordinates, 2 pi over 6. Okay, for the next pair, next ordered pair, r theta is 3 pi over 2. So what's the x-coordinate? Well, we don't really have a right triangle. You could say we have a right triangle where one of the angles is 0. But anyway, x is 3 times cosine of pi over 2. Cosine of pi over 2 is 0, and 3 times 0 is 0. So the x-coordinate is 0. And the y-coordinate is 3 times sine of pi over 2. Sine of pi over 2 is 1, and 3 times 1 is 3. So the rectangular coordinates are 0, 3. I know we can just read that from the graph. 0, 3 is the rectangular coordinates. But we want to get used to writing x in terms of r and the trig function, in particular the cosine, and similarly for y, r times sine of some angle. Okay, the next ordered pair in polar coordinates is -1 pi over 3. So what are we going to do this time? We can use a right triangle in the so the hypotenuse is 1. This angle is pi over 3. So the vertical angle, that's a term used in geometry. This angle is also pi over 3, which means this angle is pi over 6. I think I need more space. But for now, let's just do what we're going to do in a few minutes. The x-coordinate is equal to r times cosine of pi over 3. So -1 times cosine of pi over 3. And the y-coordinate is -1 times sine of pi over 3. Since the point is in the third quadrant, we know that both x and y have to be negative. Cosine of pi over 3 is 1/2, so the x-coordinate is -1/2, and the y-coordinate is -√3 over 2. So as an ordered pair, it's -1/2 for x and -√3 over 2 for y. Okay, similarly, the polar coordinates are theta are √2 and -pi over 4. So if we follow the same pattern as at least the previous two examples, then what's the x-coordinate? It's r times the cosine of the angle. So it's the √2 times the cosine of -pi over 4. And you'll recall from trigonometry that cosine of negative pi over 4 is the same as cosine of pi over 4. So why is that true? Or what's one explanation for that? The cosine function is an even function. Its graph is symmetric with respect to the y-axis. So, for example, if f of x is an even function, then f of negative x equals f of x. So that's what we have here. We have a cosine as an even function, so cosine of negative pi over 4 is equal to cosine of positive pi over 4. And the cosine of pi over 4 is square root of 2 over 2. So we just get an x-coordinate of 1 in this case. Okay, the y-coordinate is r times sine of the angle. So y is the square root of 2 times the sine of negative pi over 4. So what do we know about the sine of negative pi over 4? The sine function is an odd function. Do you remember how odd functions work? If f of x is an odd function, then f of negative x equals the negative of f of x. So in this case, sine of negative pi over 4 equals the negative of sine of pi over 4. So we can rewrite this as negative square root of 2 times sine of pi over 4. And sine of pi over 4 is also the square root of 2 over 2. And so we get negative 1 for the y-coordinate. So the ordered pair is 1 for x and negative 1 for y. That's the sort of thing we would expect with a point in the fourth quadrant. Okay, next page. Okay, derive the equations that relate polar coordinates to and Cartesian coordinates. Well, we've already done some of this. But if we have some point in the xy plane with polar coordinates, if we construct a right triangle, the hypotenuse is r. Or here we're just assuming r is positive. And the horizontal side of this right triangle is the x coordinate of this point, and the length of the vertical side is the y coordinate of that point. And as we saw, cosine of theta is equal to adjacent over hypotenuse, x over r. And sine of theta is opposite over hypotenuse, y over r. So if we solve this for x, we get x equals r times cosine of theta. Solve this for y, we get y equals r times sine of theta. Okay, so that's two of the equations that we're looking for that relate polar coordinates to Cartesian coordinates. So make sure you memorize those, or you can always just derive them if you want. Okay, what else do you think? Is there another trigonometric function that we can apply to this right triangle? Well, there's four other ones. Which one of those four do you think is the most important? So tangent of theta is opposite over adjacent. So tangent of theta is y over x. Something else. Okay, so we have three equations. Perhaps the next one is not as obvious. If we square both sides of this equation, x squared equals r squared times cosine of theta squared, and if we square the other equation, y squared equals r squared times sine of theta squared, and then if we add the two equations together, so we'll add the two left-hand sides, x squared plus y squared, and that will be equal to the sum of the two right-hand sides, so r squared times cosine of theta squared plus r squared times sine of theta squared. And then what? Well, if we factor r squared out of the right-hand side, we get r squared times the quantity cosine of theta squared plus sine of theta squared. And cosine of theta squared plus sine of theta squared equals 1. So our fourth equation is x squared plus y squared equals r squared. Okay, so that is the fourth equation that we use to relate polar coordinates to Cartesian coordinates. Okay, we'll learn how to graph polar curves. So we'll start out with the simple ones and then progress to the more difficult ones. So how do you suppose we should graph r equals 5? So something that you might relate that to in the xy plane, what does the graph of y equals 5 look like in the xy plane? It's just a horizontal line. Y equals 5 is a horizontal line. Well, we have a polar curve, r equals 5. So there's no mention of theta. So in that previous example, y equals 5, there's no mention of x. So it's assumed that x can be anything as long as y is 5. Well, for this, r equals 5, theta is not mentioned, so theta can be anything. What does the curve look like if theta can be anything, but r is always 5? Yeah, it's a circle with radius 5. Centered at 0, 0. So I should label this circle, since my drawing doesn't really look like a circle, but that's what the graph of that equation is. Okay, we have time for one more. And if we have theta equals pi over 3, there's no mention of R values. So as long as the angle formed by the polar axis and this line is pi over 3, the R values can be anything positive or negative. So when we graph this, we just get a straight line. And the angle formed with the polar axis and that line is pi over 3. Okay, that's all we have time for today. We'll do the rest of section 10.3 tomorrow. So go ahead and sign in for attendance.
Have a good day.
You too.